All right, like I was saying a minute ago, up to this point in our life, the only kind of differential equations that we can solve are differential equations where you have the derivative equals and you have only the independent variable over here. And we could solve them if they had second derivative equals independent variable. We can solve those. And again, the way we solve these, pretty simple. We wrote dy equals x squared dx, and then we integrated both sides. So our solution would be y equals 1/3 x cubed plus c. Today, and over the next week or so, we're going to learn different techniques for solving different types of differential equations. And our first type of differential equations is called separable. All right, so here's the definition. dy dx equals f of xy is called separable if the function f of xy can be split into two functions multiplied together, where one of the functions only contains the letter x and the other function only contains the letter y. So basically this is called separable if you can take this function and separate it into the product of two functions with separate variables. So the word separate shows up a lot there. Okay, so let me give you an example. dy dx equals x squared y cubed. There's a separable differential equation. Why is that a separable differential equation? In this case, g of x would be x squared and h of y would be y cubed. Max. That's exactly what we're going to do. Another reason these are called separable is what we're going to do now. Since we have this written as a product, we're going to get all the dy's and the y's on one side and all the dx's and the x's on the other side. So we're going to rewrite this as dy over y cubed equals x squared dx. We quite literally separate the variables. We put all the y's on one side, all the x's on the other. Why does that help? Now you can integrate both sides. So we're going to have the integral of dy over y cubed equals the integral of x squared dx. What's the integral of dy over y cubed? No ln in that one. I'm hearing the right answer. dy over y cubed you could rewrite as the integral of y to the negative 3 dy. So you would add 1 to your power. That would be y to the negative 2. And then divide by your new power. And then you can put it back down to the bottom if you wish. Equals, what's the antiderivative of x squared? If you get this one wrong, you're in a lot of trouble. You better not say 2x, just to tease me. 1/3 x cubed. What's the? Something about your calc. Well, that was Calc 1, so you can't blame me for that one. That's a Calc 1 problem.
I was just scared of the Calc 1 teacher.
Oh, you're scared of your Calc 1 teacher? All right, that wasn't me. So, all right. Now, if we can easily, whatever easily means, we like it if we can take this equation and we can get y all by itself. This one I don't think is so easy. I'm not sure I would get y all by itself, but I think I would write it this way. Y to the negative 2 is negative 2/3 x cubed plus c. So what did I do there? multiplied by negative 2. I have a question. On the right-hand side, when I multiplied by negative 2, I multiplied by negative 2 here.
We did C too, it just absorbed the answer.
All right, so C is just some number. It's any old constant you want it to be. So negative 2 times any old constant is still just any old constant, isn't it?
Is this like related to implicit differentiation? Seems kind of like it.
No, not really. Because for implicit differentiation, you would have a mixture. You would have like an x times a y that you're trying to take the derivative. So this is actually, in a sense, kind of the opposite of implicit, because we're getting all the x's on one side, all the y's on the other side. We're separating them as much as we can. Megan?
Do you want subscripts with a constant c that say that they're different?
No.
Okay.
And this is common in differential equations. It's kind of weird. This number c and this number c aren't the same, but we call them both c. We don't change them. And some people will call this one c, and then they'll call this one c sub 1 because they're different numbers. I don't worry about that. It's just c. JJ. Okay. I wouldn't care if you did that. Y 1 over y squared is negative 2/3 x cubed plus c. You could even cross multiply if you wanted to. So you could write 1 equals negative 2/3 x cubed plus cy squared. Okay. I guess what I'm trying to point out here is when you do these problems and you go to look up the answer in the back of the book, I don't know which form they're going to put it in. So quite often what happens in this class is people look in the back of the book and they think they have the answer wrong, but they really have the right answer that's just in a different form from the answer in the back of the book. So watch out for that. That can be a real pain in the neck. The book does some interesting simplifications sometimes. If you're taking a quiz or a test, I will accept any of those answers as correct. I won't care which one you give me. Okay? All right, here's another differential equation. dy dx equals 2x plus 3y. Is that a separable differential equation?
No. Yes. Subtract 3y. You can't multiply them.
You have to multiply, you have to have good multiplication.
Okay, so to be separable, it would have to be 2x times 3y. They need to be multiplied together. And some people will make the mistake and say, well, it looks separable because I could do this. I could write dy dx minus 3y equals 2x. And then what? Multiply by dx, and this is where people will make the mistake. People will write dy minus 3y equals 2x dx. What's the mistake I made? When I multiply by dx, I have to multiply everything on the left-hand side by dx. So I need a dx right there. Darn algebra. So that's not a separable equation. So that's one of the first things you need to learn to recognize. When are they separable? When are they not separable? This one is not separable. So we can't solve this until Wednesday. The cliffhanger. That type of equation is something called linear, and we will learn how to solve linear equations on Wednesday. All right, so how about dy dx equals, I don't know, y sine x. So a little trig in there. We all like trig, right?
Oh boy.
Separable, yes or no? Yes, it is separable. All right, so we separate our variables. We write dy over y equals sine x dx. We integrate the left-hand side. What's the integral of dy over y? ln y? The integral of sine is? Negative cosine x plus c. All right, well, I've got a loaded question for you here. When I did the integral of dy over y, back in Calc 2, if you wrote ln y, the mean teacher was going to take points off. How come? It should be ln absolute value of y.
It really doesn't matter.
What do you mean it really doesn't matter?
When you exponent both sides, it's going to be plus or minus.
So what you're saying is you want to try to get the y all by itself? So you're going to get rid of this ln and you're going to do an e?
Yeah.
All right. So when I do e on both sides, I have absolute value of y equals e to the negative cosine x plus c. And you're absolutely right. I don't need that absolute value sign anymore. How come? E to any power is what kind of a number? Positive. All right. So in differential equations, when we solve differential equations, and we end up with an ln, we typically don't need to write the absolute values, because when we solve for y, they're going to go away. Now, if you look at the answer in the back of the book, that's not how it will be written. Here's what they will do in the back of the book. They'll use the properties of e. They'll write this as e to the negative cosine x times e to the c. Because when you multiply things with the same base, you add the exponents. But then once again, c is just a number. If c is a number, what's e to the c? It's a number, so we call it c. So in the back of the book, for a problem like this, the answer would be written as c e to the negative cosine x.
Plus or minus, right?
Plus or minus. Nope, no plus or minus.
It can be, it's always positive.
It can't be plus or minus because e to any power is always positive. We do plus or minuses when we do square roots on both sides. I didn't do any square roots.
So how hard to simplify the test?
Again, on the test, I'm pretty flexible, pretty generous. I would accept any of these. Although, you're going to do enough of these problems that you're just going to get in the habit of, when you have ln of y equals something, you're going to get in the habit of just putting the c there and you'll skip those intermediates. Because it's going to happen a lot. A lot. You'll get used to that after a while.
Just jump those four steps.
We jump those 4 steps, that's it. All right, let's find some good problems in the book here. Let's see. dy dx plus 1 equals 2y. And this one has an initial condition. Y at 1 equals 1. dy over dx plus 1 equals 2y. Separable, yes or no?
Yes.
Yes. Why do you think it's separable?
Subtract.
You can subtract 1. Or I copied it out of the book and all the problems in this section are separable. So that's a safe bet. dy dx equals 2y minus 1. And then how do I separate my variables?
Multiply dy by both sides by dy.
dx, you mean?
Dx, yeah.
Multiply by dx and divide by?
Y. Or y. 2y.
I gotta divide by the whole thing. Because again, if I divide just by 2y,
You get 1 over.
I would have to divide by 2y there, and I'd have to divide by 2y there.
Oh,
So that's not going to help. What you need to do is divide the entire thing by 2y minus 1 on both sides. So we're going to have dy over 2y minus 1 equals dx. We multiply by dx, and we have to divide by the entire 2y minus 1. We integrate on the left-hand side. What's the antiderivative of 2y of dy over 2y minus 1?
Oh, one half.
1 half ln of 2y minus 1. Where'd the 1 half come from? That's a u substitution problem. You really have to let u equal 2y minus 1. du is a 2 dy. All right, equals x plus c. All right, then if I can, I'd like to get the y all by itself. Can I get the y all by itself?
Yeah, you can e both sides.
No.
Before I do e on both sides, I think I'd multiply by 2 to get rid of that fraction. So ln of 2y minus 1 equals 2x plus c. Same trick, we multiplied c by 2, but a number times 2 is still just a number, so we call it c. Do e on both sides. 2y minus 1 equals e to the 2x plus c. Same trick as the last problem. We're not going to leave it as e to the 2x plus c. We're going to write it as c e to the 2x. And then finally, add 1 and divide by 2. Answer, y equals c e to the 2x plus 1 divided by 2. That's the general solution. Now we need to find our particular solution. We need to plug in our initial condition. We're going to have 1 equals c times e squared plus 1 over 2. So 2 equals ce squared plus 1. So c is, subtract the 1, divide by the e squared, 1 over e squared. Final solution looks to be y equals 1 over e squared times e to the 2x plus 1 all over 2. Questions on that one? Okay, we were looking at this problem a little while ago. This is one of the problems out of the homework from the last section, where we decided that this equation had a solution, but we decided that that solution was not guaranteed to be unique. Yeah, I'm sorry, you have to scribble out. That's what happens when you don't use a pencil. dy dx equals the cube root of y. That's a separable differential equation, isn't it? Because you can write dy over the cube root of y equals dx. Or even better, you might write that as y to the negative 1/3 dy equals dx. You integrate, what's the antiderivative of y to the negative 1/3? Y to the 2/3, because you take negative 1/3 and you add 1, so that's positive 2/3. Flip and multiply by 3/2 equals x plus c. And again, I would probably write this as y to the 2/3 is 2/3 x plus c. Plugging in my initial condition, I get 0 equals 0 plus c. So c is 0. So, one solution to this equation is that. But as I said, we are not guaranteed that that solution is the only solution. There may be others. Sure. Anybody tell me another answer? There's at least one other answer. Not y equals x, but y equals 0 is certainly another answer.
Is y equals 0 like most likely always going to be one of the answers? Because most of them like we always put a y equals 0 as a possible answer.
Y equals 0 is not an answer to that equation, is it?
No, I guess not.
No. So, no. Y equals 0 will not always be an answer. Quite often it is. Y equals 0 would be an answer to that equation. But I don't think y equals 0 is an answer to that one. So about half the time, it looks like, from our brief survey. That's not a very good survey, is it? Other questions? All right, well, in many situations, we end up with equations that are separable. For example, if the birth rate and death rate of a population are constant, then the rate of change of population is directly proportional to the population. What does it mean to say the birth rate and death rates are constant? It's not necessarily a one-to-one. One person dies, one person is born. But the birth rate and death rate are constant, which means they don't fluctuate. So every year, maybe 5 people are born, but only 3 people die. So those would be constant birth and death rates, 5 per year, 3 per year. Okay. So if the birth rate and death rate are constant, or of a population are constant, then the rate of change is directly proportional to the population. So what's a symbol I would use for rate of change of population? I would probably use dp dt, although you had the right answer, it's a derivative. Why do I use dp dt? P is population, T is directly proportional to the population. K something. P, because it says directly proportional to the population, and the population is P. And that's a separable differential equation. You can get all the P's on one side and all the T's on the other side. So dP over P equals K dt. We integrate the left-hand side. The integral of dP over P is ln P. Again, we don't need to worry about absolute value because when we exponentiate both sides, everything's going to be positive over on the right-hand side anyway. The antiderivative of K dt is KT plus C. We exponentiate both sides. P is e to the kt plus c, which you're absolutely right. We write as c e to the kt. And it's exactly the exponential growth formula when k is a positive number. If k is a negative number, it's the exponential decay formula. It's exactly what it is. C is something important. What's C? That's your initial population. Because if P at 0 is P0, when I plug 0 in, I would have P0 equals C e to the 0, but e to the 0 is 1. So this is quite often written as P equals P0 e to the kt. So that's the population formula that you probably saw somewhere back in like an algebra class or a pre-calc class. That's where it came from. It really came from differential equations. There are lots of other things that follow this same pattern where the rate of change is proportional to the amount you have. Can you give me some examples?
Interest rates.
Interest rates. If your interest is compounded continuously, you get exactly the same differential equation. You get exactly the same formula.
Radioactive decay.
Radioactive decay, and that would be you get the same thing except k would turn out to be a negative number. Any other good examples?
Capacitance.
Capacitance?
Yep.
You have to explain that one to me because my electricity is a little weak.
I believe, like for time constants with capacitors, it's exponential growth if it's charging or decay if it's discharging.
Okay.
But it's
So-
it's a little different, but it's still.
So it must be the rate of change of the capacitor is directly proportional to the amount the capacitor can hold,
Yeah.
or something along those lines.
And I think
Yeah,
it has
like
something
E
with
to
the
the
current,
T
how
over
fast
tau.
much current's coming in.
And current.
Negative T over tau. Yeah.
Okay.
That's
Other
John
examples?
Bonk next after this.
You'll learn more about that after this class?
Yeah, we'll see John Bonk do it after.
Other examples? The other common one that I think of a lot of times is heat.
Oh yeah.
If you take something hot out of the oven, it cools, and it ends up cooling exponentially. Because the rate of change of cooling is directly proportional to the difference between the temperature and the room temperature. So you get for Newton's law of cooling, you get your original differential equation, d temperature d time is some constant times a minus t, where a is the room temperature. So it's a slightly more complicated differential equation, but it's still separable because a is room temperature, that's a constant. So you can divide by a minus t, multiply by dt, and you still get a separable differential equation that you can solve.
A is a constant as well.
A is a constant, yes. A is the room temperature. So it's a constant. You assume that the room temperature doesn't change. All right, so you're going to have some word problems that deal with these in your book. I'll just make one up. The population in Concordia, Kansas. In the year 1995 was 5,863 people. The population in Concordia in 2000 was 6,118 people. Assuming exponential growth, what is the population today? Well, we know our population formula. P is P0 e to the kt. And in this case, since we have growth, we know that k should turn out to be a positive number.
So it should be 6,118 equals the population in 1985, and just plug in T, and then just solve the K.
Correct. So what you're telling me is P0, my starting population was 5,863. So P equals 5,863 e to the kt. And then 5 years later, so we plug in t equals 5, our population is 6118. So 6118 equals 5863 e to the k times 5. And you can solve that equation for k. 6118 divided by 5863 equals e to the 5k. So k is ln of 6118 over 5863, all divided by 5. Which is approximately 0.0085. Okay. ln of 6118 divided by 5863. Yeah, I got 0.0085. So our population formula, P equals 5863 e to the kt, where k is that number there. Then how am I going to find the population today?
20 years ago.
It's 20 years have gone by, hasn't it? So I'm going to plug in t equals 20. So our answer is 5863 times e to the k times 20. So that's 5863 times e to that number times 20. I get 6951.4, so I'm not going to round it up. Questions on that?
Does that mean that the growth rate is 0.9%?
That means the growth rate is roughly 0.9%. That's correct. Other questions? What significant events happened in Concordia, Kansas in 1995 and 2000?
Probably a hurricane.
Tornado.
There was no tornado.
You were there.
I was there, that's correct. In 1995, I was hired at Cloud County Community College in Concordia, Kansas. And I taught there from 1995 until 2000.
That's why it was really familiar.
These numbers, these population numbers, I just made them up. I don't know. The population was around 6,000. I know that. I just made these two numbers up. I don't know.
How did you end up here?
How did I end up here? I actually grew up in New York State. I grew up in northern New York, up in the Adirondacks. And my wife and I decided we wanted to move closer to family. And so we looked for jobs in New York and ended up taking this one. Actually, I got hired first. She had just had our second child and wanted to take a year off anyway. So she took a year off, and then a year later another position came open and she applied and was hired. Worked out very well, very conveniently. Questions? Other questions? All right, we got time for one more word problem maybe then. All right, I'm going to steal one out of the book here. Problem 36. Radiocarbon dating. Carbon taken from a purported relic of the time of Christ contains 4.6 times 10 to the 10 atoms of carbon-14 per gram. So this is number 36 out of the book. So it has 4.6 times 10 to the 10 atoms per gram. Carbon extracted from a present-day specimen of the same substance contains 5.0 times 10 to the 10 atoms per gram of carbon-14. Compute the approximate age of the relic. What is your opinion as to its authenticity? All right, so radioactive decay we get exactly the same formula, The difference is K is going to turn out to be a negative number because we have decay. All right, so before we can answer this question, we need to know a couple things about carbon-14. What do you know about carbon-14? Its atomic weight is 14. Yeah. What else do you know about carbon-14? It's made out of carbon. Good. What's the difference between carbon-14 and carbon-12, which was the non-radioactive version of carbon?
2 neutrons.
2 extra neutrons? Protons? Electrons?
It's gotta be neutrons.
Chemistry majors?
It's neutrons. It's definitely not protons because that would change the
Okay, so the important thing to know about carbon-14, all life on this planet as we know it is based on carbon, and that's why we have classes like organic chemistry. What's organic chemistry? It's the study of how carbon interacts with everything else. That's what organic chemistry is. Everything on this planet that has ever lived had carbon-14 in it. And when the object dies, the carbon-14 decays and it turns into carbon-12. The other thing you need to know to answer this question is you need to know the half-life of carbon-14. It's a lot of years. It's about 5,700 years. All right, so that's why carbon dating is used quite often. Everything that ever lived has carbon in it, and the half-life is decent. So, if something's been dead for roughly 10,000 years, a quarter of the carbon-14 roughly is still around, so it's measurable. You would not use carbon dating to measure the age of the dinosaurs. Why not? Their carbon is unmeasurable at this point because they've been dead for millions of years. You have to find some other radioactive isotope with a longer half-life. All right, but carbon dating works pretty well for mankind. We haven't been around that long. All right, so P of T is, what's our starting amount of carbon-14?
100%. Are we doing a percent or 4.6? Oh, okay.
Well, I think we could use either number.
Our initial is
I would use the amount of carbon-14 today
as our initial.
as our initial, and then later on, T will give us the amount of carbon-14, will give us that amount. Do you have a question? Correct. I would use 5.0 times 10 to the 10 as my initial. You could use either number, but I think it makes more sense to use the 5.0, and then we'll talk about how many years from there have we gone into the past. Now I got to find the K number. To find the K number, I use this amount, this information. Half-life. If I started with 5.0 times 10 to the 10, in 5,700 years, how much am I going to have? Half of that, right? So I would have 2.5 times 10 to the 10 equals 5.0 times 10 to the 10 e to the k times 5,700. I divide both sides by 5.0 times 10 to the 10. What's 2.5 times 10 to the 10 divided by 5.0 times 10 to the 10? That's a half. It's because it's a half-life. 1/2 equals e to the 5,700 k. ln of 1/2 is therefore 5,700 k. So k is ln of 1/2 divided by 5,700. P of t is 5.0 times 10 to the 10 times e to the ln 1/2 over 5,700 t. I thought k was supposed to be a negative number. It is, because the ln of 1/2 is a negative value. That's correct. So it really is a negative number. It doesn't kind of look it the way it's written, but it really is a negative number. All right, so there's my formula. Now what?
stick in 4.6 instead of 10.
Stick in that number. 4.6 times 10 to the 10 equals 5.0 times 10 to the 10 e to the ln of 1/2 over 5700 t. I divide, I get 0.92 equals e to the ln 1/2 over 5700 t. Logarithm on both sides, ln of 0.92 equals ln of 1/2 divided by 5700 t. So t is 5700 times ln of 0.92 divided by ln of 1/2 according to science. That article of whatever it is only approximately 685 years old.
Not quite.
Not quite biblical. That's correct. Not quite biblical. Questions on that?